Session. I'm Pierre Degon from Imperial College. I'm going to chair the session, and the first speaker is Thomas Woolley from University of Oxford, who's going to speak on cellular blebs.
Oh, thank you very much. Yes, well, thank you for inviting me along to the conferences. So at the start of the year, like all of you, I'd be sort of thinking, what conferences should I go to? And nothing was really, lighting my fire. Then this one came along: pattern formation, morphogenesis, and solid mechanics. Trifecta, that's everything that I do in one single set of conferences. So thank you, Anatida, you read my mind. Great thing to be here. Unfortunately, I can't talk about all of those three things. Particularly, I won't be talking about the pattern formation much. I will squeeze it in. So what I'm very interested in terms of pattern formation are the applications. And this was one of the questions I wrote on the board. I've worked on the patterning of mice teeth, so where they're placed in the jaw. We're currently working with Dennis Heaton in Edinburgh on the whisker placode formation, and I previously worked on spots in stingrays. And the question I wanted to sort of put towards the audience and maybe biologists was, what metrics exist to be able to parameterize pattern formation models? Because on the whole, from what I've seen from the literature, hardly anyone uses anything other than the optical metric of going, well, that has stripes, my model has stripes, we're done. Beyond that, if anyone actually does try to parameterize these things, they may look at the wavelength and things like that, but it just feels unsatisfactory. And I suppose the question is, should we be trying to parameterize these models, or are they characteristics only, in the fact that you can tweak your experimental system one way, and you go from spots to stripes, say, and you can do the same thing in the mathematics? Is that the level we're at, and is that where we should stay? Or is there somewhere we can go beyond that and actually start parameterizing these with data? I haven't got the answer to that. That's a question I would like to throw open to you. If anyone got an answer now, that'd be great. You could answer that question. Sorry? What? It's on. Okay. It's on. Yeah, I was going to say that was my question I put on the chalkboard. So if anyone has an answer to that, please come talk to me. I'd love to hear your thoughts on what kind of metrics we should use to really start linking these with the biology.
Do you have experimental data on pattern formation?
Yes, so with Dennis Heaton we have the cheek there. So they take the face off the mouse and measure the interspatial distances between the placodes. But like I say, is that the best we can do? Is there something we could say to the biologist and say, actually we prefer this data? Same with the teeth. We could measure the distance between the molars. But is that the best we can do? That's my question. What I really like doing, though, is putting noise into things. And so that was my work that I did for my doctorate and then beyond. What happens when you add noise to Turing systems? That was the question. And here is one answer: not very much. You have your Turing system, as you can see here. You've got the deterministic pattern. You can see the peaks. And then the stochastic simulation around that still gives you the peaks, but it's modulated by noise. Very nice. Well, the question got more interesting when you added growth into the equation. So before I started my work, Edmund Crampin at the WCMB in Oxford, he showed that if you have Turing patterns on a growing domain, you can robustly generate pattern sequences, in particular doubling. So you can go from 3 to 6 to 12 to 24 to 48 peaks. You can keep doubling. You keep growing, you keep doubling. Nice. And sometimes you don't want this. So it seems a problem with Turing patterns that they're not robust. And what do I mean by robust? Small changes in your initial condition can lead to big changes in your final pattern. However, what we want to see is a small change in the initial condition doing nothing, because then you can use it for developmental systems, like understanding how digits form. But if you're trying to understand zebra patterning, then you want that individuality. So here's a way you can put that robustness in. My task was, what happens when you add noise? Thankfully, it broke, so I got some work to do. You still get an increase in pattern mode, so you'd get more stripes as you grow, but the synchronicity of when these appear just all falls down. So you have an insertion, a splitting, a couple of insertions and splitting there, but the whole thing is just gentle. Oh, yeah, sorry. Insert the noise. It's through a Gillespie simulation. So we're looking at the low copy number simulations. Yes, yeah. The same thing, we did compare it against Langevin equations, and also stochastic PDEs, where you're simulating the PDE, just add a random noise term in, you get the same things. So, well, I just like playing with Gillespie simulations because you know where you're dealing with there. You can write down your chemical master equation and things like that. So yeah, this is what we found. It breaks down. So what can we do? Yesterday when Sharon got us to stand up, a guy before me stood up and put his hand up and said, I work on pattern formation and noise. I was like, I'll talk to him. I spoke to him afterwards and said, hey, do you know that paper by McCade and Lugos? He goes, hello, I'm Carlos Lugos. So he's actually here today. Thank you for coming along. So if you want to know anything about this work, ask him. He'll probably be able to tell you a lot more than I can. But the idea was that we tried to understand the power spectra and how that changed with growth. And what we found that noise was doing, the noise was actually helping us. So that's an unusual thing. Most people think noise is a bad thing and we should take it out of the system because it breaks it down. And it certainly does in the previous case, I agree. But noise can help us in this situation. For one thing, noise helps us produce the pattern earlier. It pushes you out of your steady state. So here you can see the pattern is formed here, whereas it takes, what scale are we on here? Can't even tell, 10 to the something. It takes a lot longer in the deterministic system to drive you into a patterning domain rather than with the noise, because it's driving you out of that steady state a lot earlier. The other thing the noise does is it pushes you off your stable branch of your patterning trajectory. And what does that mean? That's a lot of technical terms for meaning that you consecutively increase your pattern number. Or the noise tries to. So in this case, what is happening is your system goes into a mode 3 and that stabilizes. Mode 4, mode 5 are also there, but the trajectory goes from a stable pattern 3 to a pattern 6. It misses out 4 and 5 and everything in between. The noise, on the other hand, pushes you off the stable 3 branch onto the 4 as soon as 4 becomes available and stable. So what we found is if we restrict the growth just to one edge, so in this one we're only apically growing, we're only growing at the very edge of the domain, then all we're doing is allowing enough room for the next mode to grow, and then the noise pushes us off into that mode. So again we get robustness back. We get half peak going to 1, 1.5, 2, 2.5, 3, 3.5, 4. You keep growing, you get more modes. And so, in some ways, this is an even better way of growing. Over here, there was too much noise in the uniform growth. You could insert and split wherever you liked. Here, we're only allowing you to grow the pattern at the very edge.
Does speed, velocity, does it matter?
Yes. And that's all I'll say on that subject. No, of course, if you grow faster, then if you're growing faster than the pattern has time to realign itself to the next stable mode, then there'll be a whole load of modes that it can choose from. And so wherever the noise lands between those, your guess is as good as mine. So in this one, yes, speed of growth does matter, but the idea was that we used here was just that growth was slower than the realignment time of the pattern. That's no, the Neumann.
How much of this is related to symmetry?
How much of this is related to?
Suppose you had slightly spatially varying parameters. Would you get the same bit? Because in 1D your symmetric and your solution will have the symmetry of the domain, and that might be why you see double.
Oh, I see. A lot of it, yes. The argument to prove that you're always going to double is based on symmetry. So if you break that, Edmund Crampon did this in his thesis, and what he had was he split the domain in half and had one bit growing faster than the other, and there you can get asymmetric splitting. So yeah, it's certainly down to the symmetry. It's all down to that. But this was a nice result, and that's essentially all I'm going to talk about in terms of pattern formation. The idea that noise breaks asymmetry on the uniformly growing domain, but by having apical domain growth, we can bring the robustness back. Now, we're going to talk about blebs. We had some really nice talk. We had a nice talk by Rob earlier. We had some great talk by Eva last time in the subjects. But for those of you who don't know what blebs are, I thought I'd give a brief overview to get everyone on the same page. So what you'll see in these movies is a cell. And for me, a cell is a flexible membrane attached to a rigid cortex, and then inside it's all pressurized with fluid. What Tinvez did here is that he used a laser to shoot through into the cell. The laser doesn't affect the membrane, according to him, and it breaks the cortex. The intercellular pressure pushes through into the membrane and creates a nice little blister on the membrane, and that's our bleb. So here we are. There's the laser, and there's the bleb forming. This one over here, this is the actin fluorescing, and as you can see, the actin has disappeared in this region, but over time, actin reforms in the bleb, and the bleb is retracted. So in terms of time scale, it's about 30 seconds for a production of a bleb, and about 2 minutes for a retraction. Okay? Now, these are nice experimentally produced blebs. Biology isn't nice and experimental. So these are these are the kind of cells we are actually looking at. These are from our collaborators in Reading, and these are muscle stem cells. So as you can see, you're blebbing all over the place. Again, it's the actin that's fluorescing here, but you have a nice spherical cell and roughly spherical blebs. And so the geometry is quite nice in this setting. Here's a comparison of how I see it in terms of lamellipodia and blebs. So we've heard a lot about lamellipodia. They're well-studied, actin-driven, whereas blebs have recently been rediscovered. And I say rediscovered because they were actually found at the turn of the 20th century. But it was thought that if your cell is blebbing, then your cell is dying. Get rid of it, start again, your experiment failed.
That's wrong.
Is it? That's wrong.
Before that, people thought that they were driving migration.
Did they? So there was a period where we went and say, no, actually your cell's dying. There you go, I didn't know that. There's something I've learned.
Actually, I experienced exactly that. Erich made me round for claiming that blebbing could have something to do with locomotion. My cells don't blab.
Is it? Well, they said, according to the history that I knew, there was they thought that if your cell was blebbing, it was dying, get rid of it. Then they recently discovered actually blebs are actually very useful. It can help motion, it can help cell spreading, it can help cell division. There are a lot of ways that blebs are very useful. They're pressure driven, and on the ones that we're using, there's no polarization. So the ones that Rob showed earlier, there was polarization at the front, so you had blebbing constantly there. But the cells we're working on, there's no polarization. So you can start blebbing on one side, then just stop, and then start blebbing on the other in a matter of seconds. It's just very quick and reversible. Whereas on the lamellipodial side, if you want to get to a place and you'll know where you're going, you have a source of chemotaxis, then you'll get there. Great way to move. If you're searching space, blebs are perhaps the better way to look. So the first question that was asked to us by our collaborators in Reading was that could we characterize the motion? So this is the experimental setup they have. They take muscle fibers from the mouse thigh, and they remove them in such a way that there is no damage to the fiber. These are very delicate things. If you damage the fiber, then they hypercontract and you can't use them anymore. What happens then is a cell will pop out. You'll see it here. It'll pop out here. He, she, I don't know, it. A cell will pop out here. It has a mustache, so you can tell it's a he. It will run up and down the fiber looking for damage. But as I say, in this case, there is no damage, so it doesn't find anything. There's no source of signal. If it could find some damage, it would stop, it would divide and heal. In this one, what happens is the cell gets bored and stops anyway. But anyway, so this is what we'll see here. As I mentioned, so there it is. Jumped over here, running up and down. Zooms off for a second, comes back. Here it is. There it is, running around. A friend comes in from the top to join them. And there he is, and there's his friend. He'll keep bopping around. So this is on the order of about 5 to 6 hours, if I remember rightly. And there you go. He stops, she stops, it stops, whatever, and starts to divide, and that's it done. Quick question to the audience. Does anyone think they would be able to track that automatically? I think that's too dirty. Does anyone think they... No, you're saying no. Okay. When I first saw this, I thought that's far too dirty data. I'm not going to be able to do that, but anyone think they're good enough? I'm not, it's not a challenge, but it is a challenge, I suppose, but if anyone can do it, I'd be love to talk to you. But thankfully, Reading have a lot of students, so what they did was they got the students to sit there and manually track these things. They're heroes of mine, I could not do that. They gave us the trajectory data, and the idea was simply that since there's no damage on the fiber, there's no signal for the cell to move anywhere, it's moving randomly. So here is the equation of a diffusion on a cylinder. We projected the trajectory data we had onto a cylinder, and what you can find is that if this is the equation, then along the fiber, we assume that the fiber is an infinite cylinder. Along the fiber, you have the mean squared displacement with time, but around the fiber, you have this combination of factors. It's proportional to time. And so it was a simple case of plot the data, plot the curve, what do you see? So Redding were very interested in what the difference between young and old cells were. So young cells are cells from 2-year-old mice, 2-week-old mice, and the old cells were from mice that were 2 years old. So what you can see here is the young appear to be pretty random. You know, mean squared displacement, pretty linear, that's good enough for me. Around the cell, pretty linear. Even the old cells, they seem to have this linear factor there, lux diffusion around. But what we're more interested in is the motion along the fiber, the mean squared displacement along the fiber. There you can see the old are doing something different. Now the story we went with in the paper, we didn't quite agree with, but that's the story we went with the paper. What we said was that the young cells are moving randomly. They will bleb this way because they're looking for damage. They'll bleb this way, can't find damage, then we'll move this way a bit. No damage over here, I'll bleb, bleb, bleb. Keep trying to look for damage. The old cells, when they produce their actin cortex and they retract the bleb, when they fix the damage that was done, the cortex was thinner. And so it was weaker, and so it was able to bleb more ably on that side. And so you did get a polarization almost, because you'd bleb on one side, and then you'd bleb again, and then you'd bleb again. And so you had a ballistic motion instead of a random motion. What we said was perhaps, well, maybe it could be that you've just got a delayed action. So nothing happens between here, and then here you go back to a linear case of motion, maybe random. But we went with the story of the ballistic motion because, as I say, we could see that there was definitely a thinning of the actin on one side. The next thing we did was that they treated these cells with a range of things, and then we wanted to see, could we rejuvenate these old cells? So there's the young, this HGF, growth factor human growth factor of some kind. Yeah, it brings it back a little, but not very much. PAPA, it's a nitrogen oxide donor. Laughing gas. Laughing gas keeps you young. There's nothing else you take from this talk. No, don't take that. PAPA, nitrogen oxide donor, rejuvenates the random motion and the speed, and the diffusion rate. So what's really nice about this is that there are nitrogen oxide donor medicines already out there for other reasons. So there was a bit of work in Reading, could we repurpose these medicines? But that's ongoing. So that was the first piece of work. Young cells move quickly and randomly. Old cells move slowly and have a persistent direction. PAPA and nitrogen oxide donor can rejuvenate the migration characteristics of the old cells. Very simple piece of statistical work there. Although actually, thinking about this morning's talk, it would be very interesting to go back and check the correlations because that's something we didn't do. So I hadn't realized that you might have random motion through the mean squared displacement, but not through the correlation. So I should go check that. Having done this piece of work, we then got interested in the bleb structure. What forces is it feeling? How much is the membrane stretching? How is a bleb produced? And what motivates me, even to this day, to what I'm trying to answer and understand are these two movies here. What Reading have shown is that if you treat these cells with two different things, one's treated with L-name, and this one is treated with butanol. If you treat it with L-name, the blebs become very small and almost like membrane ruffles. The cell doesn't move. Makes sense. If your bleb's too small, you don't move. I agree with that. I understand that. This one I don't understand. If you treat your cell with butanol, you can throw your bleb out further. You should be able to move further. You get bigger blebs. You get fewer blebs, but you get bigger blebs. And so that's what I really want to understand. How is structure leading to to the cellular motion? What's that connection there? And that's what I'm trying to answer. And by the end of this talk, I don't think I'll be able to answer that for you. But I'm currently working on something now which I think can. So maybe next time I'll be able to give you a better answer. But that's sort of my motivation that I wanted to give you there. Here is my cell model of a cell. This is all, this to me is my cell. To a biologist is a joke. So we have the flexible membrane attached to a rigid cortex through adhesions. The adhesions or the cortex get disrupted in some way. A bleb is formed. But this isn't where we started. This was just the schematic we drew as the first idea. But we even simplified it further beyond that. The first model we're going to use is just a single shell model, and that shell is going to be a cortex membrane hybrid. Okay? everywhere the cortex is going to, the shell is going to have one stiffness, except at the front. I weaken the front, and that's the idea of that you've removed the adhesions to the cortex in some way, and that weakened front is the membrane only, and we want to see what happens. Can the pressure push out into a bleb? So we define all our variables. We're using an axisymmetric geometry, so phi is the variable around, y and z are our Cartesian equations, theta is the normal angle, and s is the arc length variable. You draw some diagrams like this, you consider a small piece of membrane, and you can derive solid mechanics equations like this. So these all control the geometry. Lambda s is the arc length stretch, so it tells you how much you're stretching along the plane, like that. And then kappa s is the curvature, local curvature. From the geometry, you then add in some forces. Here we consider a small patch of membrane, add in the forces, so we've got the pressures, we have surface tensions, we have normal tangent forces, we have moments, and then we put them on a small piece of membrane, make them equal, we can derive these equations. So the first two are force balances. The first one is a tangential force balance, the second one is a normal force balance, and the third one is a moment balance. All very simple so far. There is a problem with these equations in that they appear to have a singularity. So as you'll see throughout the equations, we have a cos theta over y. Is that a problem? Yes and no. What you can play a little game with the equations, repurpose them and make combinations such that you can get rid of all of them except one. You're always going to have cos theta over y somewhere. But even that is not really, it's a removable singularity. It's the fact that you want to have your membrane closed at the front and the back, so y goes to 0 at the front and the back. But the thing is, if y is going to 0, then theta is also going to 0. So you just need to expand your boundary conditions near the edges. It's a technical point, and if you want to know more about that, please ask, but it shouldn't be something you worry about. It's something I have to worry about, not you. So here are the 7 equations. The first 4 control the geometry, the next 2 are force balances, the final one, moment balance. And here is what we have. Oh, I should mention, always forget to mention this. We also have a volume conservation, okay? And that is enforced through the pressure. The pressure is a Lagrange multiplier, so as the bleb expands, the back would contract to always maintain a constant volume. Now, I'm not so sure I agree with this. All the blebbing literature suggests it, or says it bluntly, saying that your cell doesn't change volume. I'm not so sure that's true, but I will agree that if it does change, it's only within a tiny %. So my verdict is still out and on. But what we do here is we have our shell, like I said, we weaken the front, and then we push the pressure forces out into the membrane, and there you go. You can see the bleb nicely forming there. But we have a problem with this, because all I'm doing is stretching that membrane at the front. Okay? Sorry?
Do you have in-plane shear in your model, or is it a fluid membrane?
Is it either? It's an elastic shell, so there's no shear in there at all. No.
No, it is it's an elastic shell. You have shear.
Yeah.
Oh, so sorry. Yes. No, I've got it the wrong way around. Yes. So yeah, it's an elastic shell, and that's what I'm doing at the moment. I'm stretching that front part. So I'm weakening and weakening. This A- parameter shows you the stiffness of my cell. A- has one value at the back, and I reduce it at the front. Weaker and weaker and weaker, bigger and bigger a bleb. That's a problem. Membrane can only stretch 4% before it tears. Which is the 4% stretch? This one. You can't even tell it's any different from a sphere. So stretching can't account for a bleb. But if you allow your membrane to stretch as far as it likes, then you can. So what can we do? We went back to the model and added in membrane growth. This is where we start allowing the membrane to repurpose itself. It can come through any source, so there's been questions about where it comes from. It can either come through endocytosis or exocytosis, some combination of those, or it could flow around the cell. Doesn't matter. As long as you have more membrane there to allow growth, we're good to have it as a source. And what we do is, this is how we input growth into the model. We start with a reference configuration, we weaken the front, and then we blow it up with some pressure. Okay, this is for illustrative purposes only. As I mentioned, this would not be as big as it would be, but for purposes of illustration only, that's as big as I'm going to draw it. What I then do is I then use the previous solution and I update it as some difference between the previous and the current solution. So there's the reference configuration, there's the solution. Here is my new reference configuration. So if I remove the pressure, this line will map onto this line. I then take that as my new reference configuration and blow it up again with a new pressure. This is delta P dash. As I mentioned, we have volume conservation. So as I increase the reference configuration, my pressure is going to have to drop because I need less pressure to go from here to here than I would from here to here. So the pressure is dropping as my bleb is pushing out. And so we just repeat that process. We iterate. We keep growing, we keep pushing the bleb out, and the pressure keeps dropping. And this is where we get to. So there are three models that I'm comparing here. Remodeling, that's the growth. Model, the no remodeling, that's me just stretching the membrane. And the geometric one, that's where I just slam two spheres together and see what happens. Can you tell the difference? So when should simplicity win out? If you just want to understand the shape and the structure, geometry is fine. A number of blebbing papers do actually say we're going to just stick two spheres together to understand the shape. Great, go for it. If you understand the pressure inside, then you can go to the no remodeling one. There you do need a bit more solid mechanics, but you can still go with the no remodeling case. Even though you're stretching the membrane, your pressure, it doesn't really change. It doesn't change from the remodeling case. But if you want to understand the pressures and the stretches and be able to quantify all of that, then you need the full power of the remodeling case. And just to prove to you here, the remodeling case and the no remodeling case, in the no remodeling case, we go up and your percentage stretch is stupidly high, far beyond anything physical, whereas in the remodeling case, we can always maintain less than 4% stretch because we're growing that membrane. I'll come back to this point at the end in terms of right versus wrong. What level of detail do you need?
The question?
Yes?
How do you explain the structure on that second graph of the...
Hands. Right, okay. You mean because what you'd expect is for it to just decrease as I grow. The problem here is the neck, okay? So I've got essentially a piecewise function. I've got one stiffness at the back, one stiffness at the front. And so what happens is as my bleb grows, it starts to bend the stiffer part. And that's why the area of stretch increases, because you have the stiffer part stretching as well. As the bleb extends, the pressure decreases, and so everything sort of relaxes. You've got the growth there on a different time scale, making sure that you never breach this 4%. In a simple answer, the reason we get this is purely because of the neck region. We did this where we had a smoother connection between the two, and we then do get a nice monotonic curve down. Why do I keep this one in? Purely so I can get a question from you. Is it numerical? Is it real? It's less than 4%. That's all I cared about. So that was the first thing we did. One shell as a cortex membrane hybrid. The next thing we wanted to look at was separating out the membrane of the cortex and putting in the adhesions. So here's the new model. We have one shell for the cortex, one shell for the membrane, and we've got the adhesions acting in between. They're acting like linear springs. And what we really want to understand is what happens when we remove a few of these springs at the front. Do we produce a bleb? Or what can happen is these springs can stretch too far, and if they breach a critical length, they break. So these are what we had: cortex, membrane, and adhesions between them. And this is what happened. We had an unzipping phenomenon. So this line here is the cortex. The red line shows you the point at which you're still attached to the cortex, and the blue line there is the bleb, where you've pulled away. As you can see, it just unzips. And this is not the shape of a bleb. Blebs are very localized, they have very tight necks, and you can have a very nice spherical protrusion from there. Not what we wanted. So how do we produce the blebs that we want to look like? So these are the types of bleb. We want to have this tight neck, very localized blebbing region, not the smooth connection that we've got there. I tried a variety of different ways to do this, and I can never remember them all, so if you'll excuse me, what I did was I altered the membrane stiff ratio, I changed the membrane growth timescale, I increased the adhesion strength density, I increased the number of adhesions in the neck only, I made the adhesion density profile stochastic, I generalized the adhesion force extension curve to be nonlinear, I varied the angle along which the adhesion stretched, and I initialized the small adhesion removal sites. There you go. None of them worked. We could not maintain a small neck bleb, as I called them. This one was the closest we got. We can sort of start seeing we have a localized neck. But that one's unphysical, because what I did there was I increased the adhesion strength around the front only. Everywhere you have one adhesion concentration around the front, I have a lot more. So as you remove some, it peels and you get to the point where the pressure and the strength of the springs can balance each other, so you never tear all the way around. But this is unphysical, because why should the cell know where to put this patch of adhesions? Because I mean, if you go back to Tinnevez's experiment where they shot it with a laser, the cell doesn't know where it's going to be shot. It doesn't even know it's going to be shot. So why should it have a region of higher density of adhesions to be able to form that bleb there? So none of those work. However, finally we found two that did. And so if you go read the paper that this is all published in, it's mainly appendices. There's about 9 appendices where I go, doesn't work, doesn't work, doesn't work, doesn't work, doesn't work, because you can't publish negative results, unfortunately. So 9 appendices of doesn't work, two results. The first one, local growth. The second one, global contraction. Very different in the way they produce a bleb. And I'm not saying these are the only two ways. I'm saying that you could have mixtures of these. You could have something completely different. If anyone has any ideas, I'm open to suggestions. I'm happy to take any ideas. But these were the only two ways that I found. So the first one, local growth. Let me give you a simulation of what's happening there. You get the unzipping, as before, but I've fixed a region over which the membrane can grow. So previously, wherever I broke away from the cortex, I would grow. I would grow along all of the blue. In this one, I'm only growing along this region. As you can see, you can support a very nice bleb there. Tight neck bleb. In the second one, what I've done there is I have reduced the pressure. So if you now break your adhesions at the front, nothing much happens. But what I'm allowing to do is the back of the cell will contract. And it's all about the time scale of the contraction and the growth of the membrane at the front. So if the back contracts quickly, you'll still have tearing, but in this case what I had was the back contract quite slowly. It pushes the membrane out, but we're always growing at a rate such that we never have to worry about the adhesions being stretched too far. So two different ways, quite opposite in the way they approach the production of a bleb, localized growing or global contraction. Do either of these make sense? Possibly. Our collaborators in Reading have shown that aquaporins highly localize to blebs. Aquaporins are recruited from the cell interior, and with that they bring, they're wrapped up in vesicles, and with that they bring extra membrane. Yep, sorry.
Sorry, are you always constraining the volume?
Sorry?
You're always constraining the volume?
Yeah, in all of these, volume is constrained. Like I say, not that I believe that, but that's what we had to work with.
Third way.
Yes, yeah, no, please, if you're third way.
Sliding attachment.
Sliding attachment, we did that. But essentially, they break. By the time they stop sliding and start realigning, your bleb's too big. We had this sort of curtain rail idea that your cells would slide along, but as the simulation progressed, they broke before they slid. In terms of the timescales that I had, so
you see in many cases actually unzipping. Okay, what
oh, okay, I didn't know that. So that's good.
As long ago been.
Oh, so you have circus motion.
circle motion. And I mean, my take on that is here your neck region consists of two mathematically defined points, okay?
In the first one, I would say yes, because that's where I'm growing over. In that one, no.
Configuration. The real cell, and you obviously have a ring.
Oh, that ring's in here, because this is axisymmetric. So in terms of the solid mechanics, the ring is there.
So okay. And then we need to discuss after.
Yeah. And I'm quite happy to, any other ideas, throw them my way. Love to. So where was it? So yes, so maybe. The idea that you only have localized growth could be the fact that these aquaporins are highly localized to a region of blebbing area, and this is why I don't believe the volume conservation idea, because aquaporins are the gatekeepers of fluid into the cell. So why would you put these gatekeepers in a bleb if they're not sucking in or throwing out water? So what the literature says, that's where we're stuck with, so that's what we do. In this one, could this be correct? Well, Eva Palak did some work showing that you do have a lot of esrin at the back which will squeeze your cell, so possibly. Either one has possibles. But how do we tell the difference between them? How can we start separating them? Well, we could look at, this is in terms of force, but I always think of it in terms of pressure because that's what I do. The pressure diagrams have very different features. They both have hysteresis, which is quite nice, because you can link that to the force, the energy lost in breaking the adhesions, which matches Guillaume Charris's estimates. In this one, so this is the local growth. First off, what you have are the adhesions being broken, so you have a rapid drop in pressure or force. Then this part is where your membrane grows, and so no more breaking. That's where the growth is. Retraction just takes you back to where you started, and no more to be said. In this case, where you have global contraction, you can support a pressure that is higher than your initial resting state. Because what is happening is, as you're retracting the bleb, you're squeezing the cell. The back of the cell is relaxing, but you're retracting the bleb at the same point. So you're retracting from the front, you're relaxing at the back, but it's still smaller than you initially were, so your pressure increases. And what we suggested here is that what you could have is bleb-induced blebbing. Whatever starts the initial bleb, we don't know. But what then could happen is that as your bleb is retracted, the pressure in the cell increases, and any local weakness, that's where you'll get your next bleb being formed because of that extra pressure inside your cell. Here we just retracted it back to its initial point and stopped the simulation. So, just to summarize what I've thrown at you today. Hopefully I don't need to tell this to you guys, but I think it's really important, as I'll mention in the next slide, is that I've come from this as a very much a bottom-up approach. I started with a very unphysical, just hybrid cortex membrane model of an elastic shell. But it worked. It got the speed, we compared it with speed data, and it worked very nicely. Membrane cannot simply stretch. Do we care about that? Well, that's a question for biologists. If they care about the membrane stretches, they need to have a more involved model. If they don't, then they can get away with a much simpler model. And finally, realistic bleb shapes, as I know it, need either localized growth or global contraction. They're the two ways that I've found. But I just wanted to give you an idea of where I am going next. And it comes back to this graph here, the one that really spoke to me, about how simple can you be. If you don't care about stretches, you don't care about pressure, you just want to understand shape, then you can fix your geometry. And so what we're looking at now is having a simple, 4 of those equations, if you remember I had 7 equations, 4 of them were geometry. If you specify your geometry now as spheres, they disappear. Everything breaks down to be analytical and algebraic. It's fantastic. You can go so far now. So what we've got here, again, volume conservation. Blebs occur stochastically all over the cell. They can expand until the pressure drops, and you'll start again, there'll be one, there's another one. The second bleb can't expand so much because all of the pressure is taken, the pressure has dropped so much because of the first one, but the first one retracts. That means you can pop a third one out. And so now we can move a lot more in terms of what a cell is actually doing by fixing the geometry. And where is this getting me? Well, now what I can do is I can link these cells onto substrates and have the idea that they're moving because of when the bleb interacts with the substrate. So what I want to, it all works beautifully analytically. I just need to sort of get this out and publish it. You can then, yeah, exactly. That's all I've got to do is publish it. What I want to now do is put them on surfaces such as cylinders, so we can now start linking the solid mechanics that we did all the way back round to the statistical motion that we did in the initial part. Because what's really great about this is that the solid mechanics properties are really hard to see. They're hard to find experimentally because it's just difficult. Macroscopically, you can see the motion characteristics really easily. Well, you saw how dirty the data was, but it's a lot easier than working with the solid mechanics. But here, using these geometric models that has solid mechanics built into it, you can link solid mechanic properties all the way to the macroscopic motion properties of the cell. And so that's what we're trying to do now. Can we understand one scale by data on another? That brings me to the end. I'd like to thank all the people in Oxford who've worked with me, as well as in Reading, who've given me their data. And yes, thank you for listening.
Questions? Yes.
Hans, yes.
So how does blebbing make the cell move along this track?
In terms of the last image, it's just purely, we did look at having adhesions, but it's purely through a touch and then an update of center of mass.
What is the bleb exerting its forces against that move the whole cell?
Well, we're thinking about it as the muscle fiber. So you have your cylinder as your fiber, and that appears to be smooth on the scale that we can see. So it must be, because this idea that there aren't any adhesions in blebbing. I can't see that happening in working in this scenario, because I mean, blebs are very good if you've got a 3D environment, you can bleb into all the nooks and crannies and move you around. The work done by Cancer Research UK, great work. They have their blebs attaching and moving them around like monkey bars. Here we're on a very smooth cylinder of a fiber. So there has to be something there sticking you down and allowing you to move onto the bleb, as we see it.
Can you do the mechanical balance that would suggest?
Yes, no, we've done that. We've done that. Well, not published yet, but.
I mean, what sort of adhesive forces are involved? Are they very weak? Or?
Oh yeah, we just need. They're as strong as they need to be. But no, they are very weak. They're within. 'Cause what I was looking at was sort of the focal adhesions that you get with lamellipodia. That's what I was comparing it against. It's within the orders of magnitude of that. So yeah.
In the living animal, can you have the same locomotion behavior? Because there the muscle fiber certainly is within a sheath of
Yes.
extracellular matrix.
In terms of muscle fibers, it's thought, I agree with you, it's not in the geometries that we're talking about at the moment. That's where I want to move to. So what they're saying to us is that it's within a bundle of fibers. So not just on one cylinder, it's got cylinders all the way around it. So it's not sort of a gel or a matrix like that. It's got these fibers all the way around it. But yeah, hopefully I will be moving towards that geometry very soon. Does that answer your question? Okay, good.
So, I mean, if I understand correctly, you model the envelope as a thin shell with variable stiffness.
So sorry, say again.
Model the whole cell as a thin shell.
The first model, yes.
Yeah. But in fact, it's a composite. I mean, you have a thin shell, which is the actin cortex.
Yeah, and that was the third model I showed you.
Next to the plasma membrane, which is a fluid.
Yeah. Well,
So
on some scale, you can treat it as a solid, flowing solid.
why don't you do a composite model?
We did as the third model.
Okay. But then I don't understand why you didn't get the neck right. I mean, this was in the first model.
Oh, sorry. There's four models here. The first one was just a composite shell. Second one was composite shell with growth. The third one was where I had two different shells: one cortex, one membrane, and then the adhesions. And the fourth one was just purely geometric. Well, I say purely geometric, but it's geometry derived through the solid mechanics. So we do get the neck when we have the membrane, the cortex, and the adhesions. We do get the neck, but we have to play around with how we get it. So that's where that slide came from, the idea of we either need local growth or global contraction.
See, the point is that in vesicles or in red blood cells, you easily get blebbing except if you have a strong shell. Okay, so the shell prevents blebbing. But I think you don't get the neck because you have the thin shell there.
We don't. We don't get. Sorry. In the first one, we got the neck because we're fixing the region over which we're softening. What we wanted to compare this against was the more realistic two shell, where we're just looking at the adhesions. We break some of the adhesions, and we wanted to see what happened. So in the first model, yeah, we get the neck quite happily, but that wasn't physical. They were only dealing with one shell, which is a cortex membrane hybrid.
I was wondering if you could speculate what could be the consequences of not preserving this cell volume.
What could be the consequences? I mean, as I mentioned, you only need a small change in volume to repressurize the cell. And I'm talking nanometers worth of difference in the back of the cell. So what would the consequences be? The consequences would be the pressure. I think of everything in this simulation in terms of the pressure. How much pressure do you need to pop a cell out, pop a bleb out? How much pressure does it produce when you retract it? I think by having your cell be more intelligent and have fluid flowing in and out, it can support more blebs more quickly. So it's purely, for me, a constraint of how many blebs I can produce. If I can repressurize myself, I can produce more blebs. I can move quicker.
Hey.
Oh, sorry, Rob, yes.
Could I tease you?
Oh, go, please.
So we used to have Wednesday talks, well, we still do, and every one of those, at the end of your talk,
You would tease
say,
people.
What was your question? Yes, we would tease people. What's the biological question?
Yep.
So I ask you, what's the biological
I would go back to that.
and what's the biological prediction? Either or.
So,
related.
the biological, well, there's a number of questions that got me to where I am now. First question is, what forces are acting on a cell to maintain a bleb? But let me go back to the point. Where I was always motivated from were those two movies. The one I understood, small blebs give you not much motion, understand that. Big blebs give you no motion as well, didn't understand that. And that's my motivation if you want to ask, what is the question? I want to understand that. I want to understand how the structure can lead to me to produce a big bleb, but then not move.
The blebs you're looking at are retracting blebs, so your answer is sort of obvious there. The cells are not making an attachment.
But why? Yeah, no, that's one way you could look at it. But from that movie, they do make they do. What it does is rock back and forth. So it blebs, attaches, then pulls off and goes that way. And then so what I'm looking at is trying to understand that in terms of the size of the bleb. Is there a critical size at which you can't support movement anymore?
Okay.
Does that answer your question?
We should stop the discussion now and maybe continue during the coffee break. So thank you very much.
Thank you.